So for the plan for today, we're going to be talking about meta-learning. And first I'm going to recap a little bit of what we talked about on Monday with regard to the problem formulation and the general recipe of meta-learning algorithms. And then we're going to actually get into approaches for solving few-shot learning problems. And so this will cover what you'll be implementing in homework 1, although actually I think I saw a couple people already turned in homework 1, so maybe you've already implemented it. And by the end of the lecture, you'll be able to implement few-shot learning algorithms and allow neural networks to do the kind of few-shot learning problem that you did on the very first day of class. Cool. So let's get into a little bit of the recap. So on Monday, we talked about the meta-learning problem, where our goal was that we were given some data from some set of tasks, and our goal was to solve a new task with less data at a higher level of accuracy or more stably. And in the context of this course, we'll mostly be considering trying to learn tasks more quickly, that is with less data than if we were training from scratch. One of the key assumptions that I mentioned is that the tasks should be drawn from the same task distribution. This is an assumption that's needed to show that these algorithms might generalize and be able to learn new tasks. Although, of course, in practice, it's a little bit difficult to sometimes actually realize this assumption in practice. This assumption is basically analogous to the standard IID assumption that you see in machine learning, where you assume that your training data points and your test data points are drawn from the same distribution. And so you might have some distribution over tasks. You're given some training tasks from that distribution and a test task from that distribution. Like before, we want the task to share some structure, and the task could correspond to lots of different things. So in homework 1, the task will correspond to recognizing handwritten digits from different languages, shown here. We'll also look at an example where different tasks correspond to giving feedback to students on different exam problems or different assignments. We'll look at one example where the goal is different tasks correspond to different regions of the world, and you might want to classify species in those different regions of the world. And the task could also correspond to something like robots performing different tasks. Now, a natural question to ask from here is, okay, we need a set of tasks in order to learn a new task. How many tasks do you need in order to be able to quickly learn a new task? There isn't really any cut and dry answer here, but in general, the more the better. In machine learning, the more data you have, the better off you'll be. In meta-learning, the more tasks you have, the better off you'll be. So essentially in meta-learning, we're treating data points we're essentially treating tasks as data points. Yeah?
Any kind of assumption, because like, if the test task is also coming from some kind of similar distribution as the training task, then like how is it exactly a new task? Is it like a new area of the distribution that we haven't explored in the training data set? Like how is it different from the normal task that we're training on?
Yeah, so I guess we can draw an analogy to machine learning where maybe we have a lot of images taken from the internet, but then we ultimately will want to pass in new images into our machine learning model. And so those images don't match any of the images that are in the training data set. Here, maybe, as one example, maybe different tasks correspond to different users. So you want to build a spam classifier for different users, and then the test task will be a new person. And it will be a person that wasn't in the training data set. And it will be trying to classify spam versus real email for that particular new user. Does that make sense? So it'll be something that is, it should be generally similar to the kinds of things that you've seen before, because we want to, that's going to let us generalize to that new task with a small amount of data. But it is going to be, it can be something that's new, that's fundamentally not seen in the training data set. Yeah?
Can meta-learning be applied to tasks which are seemingly unrelated at face, but maybe you could like potentially exploit some sort of like unseen shared structure to use one task to help you do the other?
Yeah, so the question was, can meta-learning be used for two tasks that have kind of seemingly very little in common, but perhaps maybe there is something that it can discover that they have in common? So first, if you only train on 2 tasks, then generalizing to a 3rd task will be very difficult. But I'm not sure that's exactly what you're asking. If some of the tasks in your distribution are very different from one another, and you have more than 2 tasks, then meta-learning will try to find the common structure between them in a way that allows it to very quickly solve those tasks. And so, yeah, and if there is shared structure, then it's explicitly going to optimize for trying to find the things that are in common between those tasks. Yeah.
So in that case, if there actually isn't much shared structure, would it be could it be detrimental to actually use meta-learning?
So if there isn't that much shared structure, would it be detrimental to use meta-learning? So I don't know if it necessarily be detrimental in the sense that it may have a hard time finding that shared structure. In the worst, well, I guess we'll get into this when we get into the algorithms, but there are some algorithms where they will essentially revert to learning from scratch. And so you won't do it worse than learning from scratch, whereas there are some algorithms, including the ones that we'll talk about today, where they could do worse than learning from scratch. Yeah?
Are the data sets for each of the tasks in the training set about as large as you would need in like a normal machine learning task, or can you do with less data per task?
Yeah, so one of the things that's really cool about this is actually you can get away with much less data per task than if you were to train completely from scratch. And so we'll see this actually in one of the data sets, including actually the data set that you'll use in your homework. Cool, so one of the things that we talked about on Monday is that there's a couple different ways that you can view meta-learning algorithms, one from a mechanistic standpoint and one from a more probabilistic standpoint. And from the mechanistic standpoint, you can think of meta-learning as basically trying to train a neural network to read as input data and give you predictions for new data points. And so you can think of it as implementing a learning procedure. Whereas the more probabilistic view is thinking about how we may try to extract prior knowledge from your set of training tasks and impose that prior at test time when trying to learn so that you can learn with less data. In the next few lectures, we're going to really be focusing on the mechanistic view, which will make it easier to think about how to actually implement these algorithms in practice. But we'll come back to the probabilistic view in a few weeks. So, and then lastly, the last thing that we talked about on Monday was looking at an example, a few-shot classification example, where ultimately we wanted to be able to classify new examples, shown on the right here, given a very small training data set. So the training data set only has 5 data points, and we want to be able to use that training data set and previous experience from other image classes in order to effectively solve and make predictions for new test examples. And so the way that we can do this is construct tasks that look a lot like this test task. So construct training sets and test sets from other image classes, from other experience or data that we might have. Run kind of meta training on these tasks such that when we see a new task at meta test time, we can learn from this tiny data set and make predictions. Now, and this is kind of an image classification example. We can consider this for other machine learning problems as well. Now, what I'd like to talk about next is first getting a little bit into some of the terminology that's used in meta-learning in the context of this example, and then we'll dive a little bit more into the setup. So we have the setup where we have a number of different training tasks. For each of those tasks, we have a training data set and a test data set. These are sometimes also called the support set and the query set. The support set you can think of as kind of providing support for the learning process, and then the query data set will be used to query the predictions of the model after learning on the support set. Using these latter terminology can be somewhat helpful to differentiate between meta training and meta testing. So we've talked about this notion of few-shot learning, and so you can think of this as k-shot learning, where you have k examples per class. Or if you're in a regression scenario, you have k examples total. So this is k-shot learning means you essentially have k examples to learn from. And then we'll we'll use n typically to denote the number of classes that we're trying to classify between, the number of classes that we're choosing between. So with that in mind, I have a question for you. So maybe I want to ask you, what is k and n for this example? And so first, in terms of k, maybe you can kind of raise your fingers and kind of say what you think. Actually, let's actually start with n. So maybe raise your hand with fingers to denote what you think n is for this example. Cool. So I'm seeing a mix of 5s and 2s, but mostly 5s. Cool. So in this example, we're doing n-way classification. I guess, so yeah, the mix of 5s and 2s is, I can see where you're coming from. So this is a 5-way example because we have 5 different image classes shown in the left training data set. I'm only showing 2 test examples here just in terms of space on the slides. But there are kind of 5 classes underlying these training data sets. And then can you put up a show of numbers for what k is? Cool, I'm seeing 1s, which is good. So yeah, we're giving it basically one example of 5 different classes. So this is a one-shot learning problem where you have one example per class. And we're trying to solve a 5-way classification problem. Cool. So that's a bit of the terminology. Now, in terms of the kind of general recipe, or maybe another view on the meta-learning problem is if you think about supervised learning, our goal is to map from inputs to outputs, and to learn a function that predicts the output given the input. And we do this with a set of input-output pairs, XY pairs. Now, in meta-learning, we can also actually frame it as somewhat of a supervised learning problem, where our inputs are going to be a little bit different. So our inputs are actually going to include the training data set for a task, as well as, in that training data set, we'll have k examples, or k examples per class. And in addition to a training data set for that task, we're also going to have a new test input that we want to be able to make predictions for. So the training data set is essentially what was in the green box on the previous slide, and the test examples, or the test example is one of the things that was in the blue box on the right. And then we want to be able to predict the label for this test example. And so you can think of this, this green arrow here as the process of learning from that data set to make a prediction for a new example. And from this standpoint, we could actually, again, view this as a supervised learning problem where we want to train a neural network to take as input a data set, learn from that data set, and make a prediction on a new test example. Now, how do we go about learning this kind of function? Well, instead of having a data set of input-output pairs, we're actually going to have a data set of data sets. And each of these data sets has to have has to have more than k examples so that you can sample k examples to be used for the training data set, and at least one example to be used for the test set. Yeah?
So I had a question with the notation that I'm using. So for the one-shot classification, generally in the testing set, we have one example of the classes that we are going to test for. So like we have one, let's say if I want to classify between cats and dogs, then I will have one example of cat and one example of dog. And that is what we'll be testing on. But what you are using, that seems like a zero-shot learning, where you are not using, like you have 5 classes in test set of 5 different classes, and the actual, what you're actually classifying for are 2 different classes.
Yeah, so going back to the slide here, or this visualization here, so the number of examples in this red box here doesn't matter too much. This is you need there to be at least one example, and you need to be able to And in general, your test set is going to be larger than 2. You'll probably have at least 5 examples so that you're actually like evaluating its ability to make predictions for all 5 classes in your training data set.
Do we need the 5 support classes there for the testing part in one-shot classification? Speed of pre-trained model and like the model itself and just the classes that you're going to classify on, the data from the classes that you're going to classify on. Why do we need other classes in testing?
Oh, so I guess what I'm visualizing here is a 5-way classification problem. And so you have one example for 5 different classes. And so it's a one-shot learning problem. And then technically, if all you cared about was to classify these 2 images, then it's actually a 2-way classification problem. I would have shown all 5 examples if I had a little bit more space on the slides. But yeah, I'm trying to frame this as a 5-way problem. Yeah. So you can sort of just think of this as having like, you can imagine if there's like 5 examples here. Yeah. Cool, and here I'm actually only showing one test example in terms of like what this function needs to produce. But then when you actually train this function, you'll actually sample more like different test examples to evaluate its ability to generalize given a training example. Or giving a training set. Okay, and so we can learn this function with a data set of data sets. So a set of data sets where each data set is for a particular task. And again, this data set, the data set for a given task I should have more than k examples so that you can use k to be used in the training data set and some other examples to be used in the test set to measure generalization. Yeah?
There are 2 different, there are 2 different subscripts here. There is an I and there is a J. So I corresponds to the task, and the J is the
Number of examples.
Okay.
Yeah, so here the I is indexing the number of tasks, and J is indexing the examples that we have within a task data set. Cool, and so one thing that's nice about this kind of view is it means that now, in order to implement a meta-learning algorithm, all we have to do is design this function f that can read as input a data set, and then optimize that function f. And so essentially in this lecture and the next 2 lectures, we're going to be talking about different ways that you can design and optimize this function f. And so in particular, kind of the general recipe that you can think of for designing a meta-learning algorithm is choosing a form of this function. In this lecture, we'll see a form of this function where it's just represented by a neural network, but we'll actually see other forms of this function in the later lectures where f could correspond to running gradient descent, or f could correspond to an algorithm like nearest neighbors. And then once we have that function, then we're going to optimize the free parameters of that function, which we'll refer to as the meta parameters, using the meta training data. Yeah?
the test data of the test task, or is it the train data of the test?
Xtest is the test data for the task that is specified by dtrain. So dtrain and xtest are both from the same task. And so that could be, if you're during meta training time, that's going to be one of the meta training tasks. If you're at meta test time, that's going to be one of the new tasks that you haven't seen before. Yeah.
In the previous slides, what is the K?
So K is the number of examples, like in K-shot learning, it's the number of examples that you're going to be learning from.
Or for the beta supervised learning, each iteration we sample a tuple K from the training.
Yeah, actually, so there's a question of how do you choose K? Typically, if you have a sense for how many, if you have a sense for like you want to be able to do one-shot learning, then you'll just set K to be, essentially to be 1 per class. and then at test time you'll do one-shot learning. You could also have k be variable. So you could actually sample different k for different tasks and have some tasks be one-shot learning tasks, some tasks be 5-shot learning tasks, such that you're preparing your network to be able to do one-shot learning and 5-shot learning at meta test time. Yeah.
X be nk instead of k because
Yeah, so the question was, shouldn't the index here be n times k rather than k? So if it is a classification problem, then it should be n times k. If it's a regression problem, then the standard notation is to just use k. And so I use k here, but it kind of depends if it's a regression or classification problem. And the convention for that is one-shot learning you typically think is learning from one example, and in regression problems, you can actually, well, learning from one example in regression, probably you won't get very far, but that one-shot learning is learning from one example there, whereas in classification, if you have only one example, it's fundamentally impossible to solve like a 5-way problem with just one example, and so the kind of convention is to use, to have it be per class there, and so if this was classification, the k would be n times k. Yeah?
You mentioned if you're trying to train one of them to be like a one-shot task, just 3-shot tasks, if you have a large data set for these tasks, would you be training them differently for a one-shot or a 3-shot?
So we'll get into methods in a second, but it basically corresponds to how many, like what is the size of the data set you're passing into your function. And well, so basically you can train this function to take as input variable size data sets. And that's useful because at test time, if you're not sure what size your data set's going to be, then your function should be able to handle different sizes. Yeah.
So in the last class, when we were talking about the probabilistic view of meta-learning, we kind of talked about theta, which were the parameters representing the shared structure, and then also phi, which were, I guess, the task-specific parameters. So in this case, is f representing both theta and phi, or like, is it just representing theta?
Yeah, so the parameters of f here are theta, and that is kind of representing the theta that we saw in the previous lecture. Here, you don't see phi appear here, and that's because phi is, we'll see in some algorithms phi will come out explicitly, whereas in other algorithms we won't be explicitly representing phi. And so it's useful to set up this notation in a way that can either have it or, well, that doesn't actually explicitly represent it, because some of the algorithms we'll look at next week don't actually explicitly represent what phi is.
I see. So if it's not explicitly represented, does it just mean that it's like a part of theta in some form, or like what would that mean?
Sort of. Basically, next week we'll cover non-parametric meta-learning methods, and so those don't actually have explicit parameters, and so phi won't ever appear. But we'll get into that on Wednesday next week. Yeah.
Just a quick clarification question. The X, TS, is that the task label?
So X-test is a new example, a new input for that task. So it's given a data set, given a task data set. Here it'll basically just correspond to one of the X's in the task data set. Cool. So I think that we should start kind of running into like approaches, because I think that will also clarify the setup as well. And so we're going to start with a running example, which is going to use the omniglot data set. And you'll be actually using this data set in your homework. It's actually a pretty cool data set. It has a data set of 50 different alphabets, written alphabets. And it has a total of 1,623 characters across all of those alphabets. And they're all written by hand by people. And here are some examples of some of the alphabets represented in that data set. And per character, there's actually only 20 examples. So this is getting into one of the questions which was mentioned before, which is that typically in a machine learning data set, you wouldn't have only 20 examples per class in your data set. For example, in the MNIST data set, I think it has like on the order of thousands of examples, maybe tens of thousands of examples, or maybe like 6,000 examples per class, I think. So you can sort of think of this as the transpose of a data set like MNIST, where instead of having many examples and a small number of classes, you actually have a large number of classes and a very small number of examples per class. And I also think that the statistics of this kind of data set are a little bit more reflective of the real world, because in the real world, we don't see like 1,000 forks and 1,000 notebooks and 1,000 pens and for only a small number of things. We actually have a really massive number of objects, and we only kind of run into those objects a small number of times in general. Cool, so we're going to be using this data set, and in this data set, to start off, we can think of different tasks as different alphabets. And let's think about how to actually set up the kind of the meta-learning thing here. So we're going to be looking at a three-way classification problem, just because then I don't have to draw as many images. And we're going to be looking at a one-shot learning problem. And it's worth mentioning that there are two different versions of black box meta-learning algorithms, and so we'll cover both of them. And first we'll talk about kind of the meta-training process. So the first thing to do during meta-training is to sample a task. And so this will correspond to sampling an alphabet, and specifically sampling 3 characters from that alphabet. And the reason why it's 3 is because we're just going to be considering a 3-way classification problem. And then once we've sampled a task and sampled the characters that we're going to be classifying between, we're going to sample 2 images per character. And we're then going to break these examples into a train set and a test set. And so, for example, maybe the alphabet that we sampled is the alphabet that we use in English. And the 3 characters that we sampled were A, B, and C. And we're going to sample 2 different images per character so that we can use one for a training data set and one for a test data set for that task. So these are maybe, 2. This will be our kind of D-train for task I. Maybe we sampled task I. And this is going to be D-test for task I. Now, one thing that we're missing here is we're also missing labels. We need labels in our train set and test set. And so what we're going to do is we're also going to assign labels to each one of these. So we can say label 0, 1, 2. It's important to have consistent labels across our characters. OK, and now we get to the fun part. So what we're going to do is we are going to pass our training data set into a neural network that will implement the learning process. And so in terms of passing this into a neural network, these data sets may have a number of different examples. And so things like a recurrent neural network are typically a good choice, or a transformer if you want to be a little more into the times. And so you'll pass this into your training data points into a recurrent neural network. And at this point, we're going to get to kind of the 2 different versions. So one version of black box meta-learning will take as input these training data points and output a set of parameters. And we'll then use those set of parameters to classify new examples from our test set. And so in particular, I'm going to need to work on my space management. So we'll take these set of parameters. We'll then pass as input one of our test examples into a neural network with those parameters to get a prediction for that test example. So this will be x test I. This will be y hat test I. And then we'll compare this to the corresponding label for that example. And then what we can do is once we compare our prediction for this example to the label for that example, we can backpropagate through this entire neural network into the parameters to train this neural network so that it can learn how to learn from this data set. And then once we then kind of backpropagate into the neural network, update the parameters of this network here, which will be the parameters theta, we'll then kind of, this is step 3, then we'll go back to step 1, sample another task, and iterate the process. So this is the meta training process. We can talk a little bit about the meta test process before we move on to the second version. But yeah.
From the tested A, just the neural net or the neural net and the classification.
Does it go through the neural network or does it go through the neural network and the classification?
Go through just the RNN and everything else that you worked on over there.
So it's basically going to update all of the parameters of this network. And one really, really important thing to note is that it's not going to update phi. So phi you can think of more as an activation of this neural network. It is only going to update the meta parameters of this network. So we're going to differentiate through phi into the parameters of this thing right here. I really should have brought some more colors today, but you can think of the parameters. The parameters of this will include like both the encoder as well as kind of the kind of recurrent parameters as well. Yeah.
Recurrent neural network here?
Yeah, so the question is, why does it make sense to use a recurrent neural network? You can use other networks as well, and we'll talk about some other choices. You could use something like a deep set architecture or a transformer. One thing that is convenient about sequence models in general is that they can handle variable length sequences. And so you can pass in like variable length data sets, for example, and it should be able to handle that. In general, architectures for handling sets and sequences are pretty good choices. Yeah.
How general, I'm not sure if generalizability is the right term, but like if we do the training with 3 classes and test with like 4 classes, would it still work or will crash? If you have like a transformer,
Yeah.
based model probably is not flexible enough to do that, but for like the current model.
Yeah, so the question is, if you do meta training with 3 classes and then evaluate this ability to learn with 4 classes, then how well does that work? In general, probably not very well. It depends on the architecture choice that you choose, but you're basically training a recurrent neural network, and if you train a recurrent neural network on a sequence length of 3 and then test it on a sequence length of 4, you're basically testing it on something that it hasn't been trained to do. Yeah.
Do you need test data for your training tasks, or can you do this in an unsupervised way where you're just hoping to learn like how to cluster them?
Yeah, so the question is, do you need test data, and can you do this in an unsupervised way? There's lots of different variations that you could consider here. You could consider something where the training data set is maybe unlabeled and is trying to but the test set is labeled, for example, and is trying to cluster and so forth. We'll get into some more advanced kind of variations of this in some of the coming lectures. But in the basic setup, it's good to have labels are helpful. The other thing that I'll say is it is important for these to be held out examples and not just the same examples as what you pass in, because if you pass in exactly the same this example here, instead of learning to learn, it will learn to memorize, and it will learn to just exactly only be able to make predictions for the examples that you passed in. One other note that I should mention here is that here, note that we're passing in both X and Y. We're passing in both the input and the label into the recurrent neural network. Here, it's important not to pass in the label, because if you pass in the label, then it will just not look at the image and predict the label. And this is something that you'll run into in their homework. It's a kind of common mistake to accidentally pass in the label into the network here. Yeah.
Shouldn't the prediction for each sample be independent and irrespective of the order? So why are we treating it as a sequential problem? Because if I have a CNN for each image and they're predicting independently of the sequence, isn't that the true test of task?
Yeah. So one downside of using an RNN is that the ordering of these data points matters, and in practice, this is a set, and so the order of examples doesn't matter. We'll get to this in a few slides, but the architectures that like deep sets that are permutation invariant are actually can be a better choice than an RNN for that reason, because they'll encode the fact that the ordering of the data points doesn't matter.
What exactly are we predicting the parameters, which is the file here? Like, if so, how many parameters do we predict? Or what are we predicting?
Yeah, so here it is actually, it's predicting parameters that are being used to make predictions. And so this is in general, a pretty high dimensional vector. And so it may correspond to, like, yeah, the parameters of a neural network. I guess I'll get into version 2. So that was this was version 1. Version 2 is something that is a little bit less unwieldy. So predicting like millions of parameters with a neural network can be rather expensive. And so what you can do instead is, let me write these out again. You don't have the label for this. So what you can do instead is you can simply use something like a recurrent neural network and actually just continue running that recurrent neural network here. And in this case, the phi I is more implicit. And here you'll again be asking it to predict yi test for this example right here, which is xi test. And this is something where you don't actually have to have your RNN output a huge parameter vector. You can just have it output, say, this is like the hidden state of your RNN after like 3 examples. And you could sort of think of phi I as like the set of like these hidden parameters as well as any parameters that are in this network right here. So we can maybe refer to this as like theta g in the sense that if this is like a function g, those are the parameters of that function. And so this is what like phi I would be in that case. And in this case, this is a lot nicer because this is going to be used more in practice than this version because then you don't have to output like millions of parameters of a network. You can actually, you can actually like only represent a much smaller context here. Yeah.
So are the task-specific parameters in output of the shared model theta, or are they the result of adapting theta by something like gradient descent?
Yeah, so in this lecture, the task-specific parameters are the output of this neural network model here or here. I guess we can call this HI in the sense that this is kind of a context vector. In the lecture on Monday, we'll see examples where the task-specific parameters are the result of something else, like running an optimization like gradient descent. Yeah.
Why is it not important to train phi I in model 1?
Why is it important to?
Not basically backdrop on phi i's too when we're updating all the parameters.
Yeah, so the question is, why is it important to not update phi I? So I think that maybe, so in this example, it may be a little bit more clear in the sense that when we run gradient descent to kind of test generalization in this case, we're going to backprop into all of the parameters of this RNN, but we're not going to update HI, because HI is an activation. And when you have the activations of a neural network, you don't update the activations, you only update the weights. And so analogously, in this example, you can think of phi I as the activations of your neural network. And so you're not going to be updating that, you're only going to be updating the weights of this neural network. Yeah?
Can you just say one more time what the difference is between 1 and 2?
Yeah, so the difference between version 1 and version 2 is they are very similar. The main difference is that in this case, this neural network right here, the only parameters making predictions from this example to y test are going to be phi I, and those are going to be outputted by this. And so those are going to be the activations of this RNN. Whereas in this case, some of the parameters are actually going to be, some of the parameters here are actually going to be optimized as part of the meta-optimization. And so, for example, the encoder of this RNN may actually be shared across the time steps. And so you basically have more parameter sharing in this version. Yeah.
But what if you're still not backpropagating through the test label, right? When you're optimizing theta g, you're still optimizing on the 0, 1, 2 from the train set. You cannot do backprop with the test labels, right?
So you're asking.
How do you optimize theta g basically? Like, because if theta is just, phi I is just being predicted from the RNN. But is theta g, you have to be, like, they have to be optimized, like backprop. So.
Yeah, so in this case, theta g will also be optimized with backprop as well, but hi will not be.
The training like sequence.
It'll be optimized with respect to this the loss here.
But then you're using the test labels to optimize, right? Like the test set labels.
You can basically think of all of this as the learning process, and we're optimizing all of the parameters of this learning process with respect to how well it generalizes on a new test example. The one thing that you may be noticing here is that it could be that the neural network could just ignore all of this and just learn a classifier for it. And that's actually a problem that can come up in meta learning. And so one thing that I'll mention here is that here we assigned labels somewhat arbitrarily, like 0, 1, 2, in the order of the alphabet, but really that was somewhat arbitrary, and when you're given a new alphabet, you don't know what is the first letter of the alphabet versus the second versus the third. And so what we'll do in practice is when we assign these labels, we'll assign them randomly. And so when we sample a task, in this case, I assign this labeling, but when you sample this task the next time, you might sample a different labeling where you have, for example, 1, 2, 0, 1, 2, 0. And as a result, when you actually randomize that, that prevents the neural network from just memorizing a mapping from the input to the label and ignoring the context.
So as a follow-up, are we also allowed to optimize phi I on the test labels as well? Are we allowed to do that?
So
Phi I is more similar to hi here. Phi I is an activation of the neural network rather than some of the
weights.
Which can also be optimized, right? It's parameters of some other network.
So it's the output of this. It is the parameters of a neural network, but it's the output of our recurrent neural network. And so we're setting it to be the output of this neural network. And so if you updated it one round, then the next round it would just be wiped by a forward pass of the RNN. Yeah.
So just answering this question, could it be because in meta training, the regime of training is very different from the normal training that we see in machine learning. So in meta training, we see even in training, we have two subset of, for each class we have two subset of sample supported query, which is training and testing. So although it is said to be testing data, it's not actually testing data. We use it to train our model.
Yeah, that's a great point. So to kind of reiterate, when I'm talking about this is our task test set for task I, and we are going to be training the parameters of our RNN with these test examples. And that may sound like a really bad thing, and it sort of should sound like a really bad thing because we're going to be training on these test sets. But in meta learning, actually, the real test is new tasks. So this is the test set of the training task, or one of the training tasks. And then we're going to be given new test tasks, and those are going to be really the real test for these models. Yeah.
So is there a risk of catastrophic forgetting in this sort of setup? Like when we're sampling new tasks and then updating the same parameters across tasks, how would we prevent forgetting from happening on the previous tasks that we've seen?
Yeah, so the question was, is there a risk of catastrophic forgetting in this case of past tasks that you've seen? So in practice, when we sample tasks, we'll sample them from a set of tasks, and as long as you keep on sampling from that task IID, then you should be able to remember those tasks. I should also mention here, I said that we're just going to sample one task. In practice, you can sample a mini batch of tasks, so multiple tasks, and that will give you a lower variance gradient. And so similar to in machine learning, if you're sampling IID from a training data set, you don't have to worry too much about forgetting. We also don't have to worry about that too much here. But if we did have a sequence, like a non-stationary sequence of tasks, we might start forgetting some of the older tasks if they don't keep on reoccurring. Yeah.
What's the point of using a recurrent neural network rather than another kind of network? If because you see that the data are not really related, right? I mean, there's not a direct relationship when you're trying to translate something. And so why are we using a recurrent network instead of another kind of network?
So you want to have some sort of network. The question is why are we using an RNN versus some other sort of network? You do want this network to be able to take as input a data set. And data sets, so you want to be able to process some sort of set of examples. And so things like RNNs are a good choice for modeling. Well, they're actually not, in practice they're not a great choice, but they're the simplest choice for modeling sequences. And things like transformers and deep set architectures and like 1D convolutions could also be used as well. You wouldn't want to use like a feed-forward, so one thing you could do is you could use a feed-forward fully connected network and basically concatenate the embeddings, concatenate all these images together and pass it through that way. And that might not be a great choice compared to something that explicitly models these as separate entities. Yeah?
In practice, does version 1 work with very high-dimensional phi?
So yeah, in practice, does version 1 work with very high-dimensional phi? So there are some papers that have actually gotten it to work pretty well. In practice, people typically use some form of sharing across layers so that you're not outputting the entire parameter vector all at once. You might be outputting like one layer at a time, maybe telling the network which layer that it might be outputting. One paper, or one thing that this is often referred to is a hypernetwork. And a hypernetwork is basically any sort of neural network that's outputting the weights of another neural network. And it can be used for meta learning, but it can also be used for other things. And so there are some examples of it working well, but also in general for few-shot learning problems, this is the more practical solution. Cool. I have a couple examples of other data sets on the slides if you're interested in exploring that for your project. But for now, I just want to, I want to recap some of the stuff on the whiteboard, but also we've talked about meta training. We haven't explicitly gone through what meta test time looks like. So let's also quickly do that first. So at meta test time, you're actually just given a test task, and you're also given a training data set for that test task. And so, for example, maybe your data set is of the Greek alphabet, and so you have some examples like this. And then you're probably also given some test examples. So maybe you're given an example that looks like this, and you want to be able to classify this example given your few training examples. And so does anyone want to kind of say what we might do at meta test time? Yeah?
We put the training data set, like the alpha images that we have, the information, and we use our parameters that we learned with, and also we input the testing image, query image, and then we see where does we get the highest score, so that we can classify.
Yeah, so what we can do is we can pass our training data set into our recurrent neural network, also pass as input our test example, and ask it what the corresponding label is. So we'll probably be given corresponding labels for this, like 0, 1, and 2, and we will pass these into our neural network. Doesn't have to be an RNN. And then also pass as input this example, and then hopefully the neural network will output 0, insofar as that looks like an alpha.
So for the training set in this case, we have kind of like multiple passes, or will we like continue with the one shot thing of like just pass alpha with the label 0, try to predict that, update that, and then try on the second XPS thing?
So in black box meta learning, what you'll do is you'll always pass in the whole training data set as input and then pass in the test example. Another method that we'll see next week is something that actually makes explicit comparisons between the test example and the training examples. Does that answer your question?
How interesting tuning happening because of the training set that we're posting in this?
Sorry, can you repeat that?
Sorry, is there any tuning, fine tuning that's happening because of the first alpha beta gamma thing?
Yeah, I understand now. So the question was, is there any like parameter updates or any tuning that's happening when we do this? And the answer is no. So we're just doing a forward pass through this RNN. And so we're not actually, you can think of this RNN as kind of implementing the learning process. And if you give it a big enough neural network, these neural networks can learn in that way. And so there isn't actually any sort of parameter updating other than perhaps you can sort of think of the hidden state as being updated as you pass it through the recurrent neural network. Yeah?
Why don't we implement, or why don't we have any algorithm which doesn't do the fine-tuning?
So you're asking why not have an algorithm that does do some amount of fine-tuning?
Do something with the information that we have. I know we are already using alpha beta gamma to compare our results, but more than that, is there any algorithm?
Yeah, we'll see that on Monday, next week. Yeah.
So here the RNN is predicting the parameters of a model without actually knowing about like what is the architecture. Like, is there some kind of model that is easier to learn, like the parameters that we're predicting? That would depend on like the kind of model that we have, right? Like the architecture or something. So
generally, for version 1, the architecture of this function right here will be always the same. It will be fixed.
Yeah, but is it like some kinds of architectures are easy, like phi, to learn phi, some kinds of architectures are easier to learn, like predict phi for or something like that?
Yeah, so you're asking, are there some architectures for which it'd be easier to predict phi I than others? Generally, the smaller the architecture, the easier. And if you only have to predict some of the parameters of the architecture, which is similar to here, like for example, you could have it only output, like H could correspond to like the last layer of this network, and then you only have to predict like some part of it, for example. Yeah.
In this setup, I actually have two questions. First question is, you referred to this as black box. What about this as black box?
Yeah, so I'm calling this black box meta learning because the learning process itself is somewhat of a black box. It's just this big neural network. I guess it's multiple boxes on the board, but you can think of this as just one kind of monolithic neural network, and we don't have a lot of, we don't see a lot of what happens inside this neural network to actually interpret how it's actually adapting or learning from these examples.
And then my second question is, once the hypernetwork predicts phi I, does phi I get updated at all by like this other process over here, or is it just static? It's static.
So it outputs it once, and then we make predictions with that, and so we can predict this example, and also make predictions for the other test examples. And it will only be changed once we pass in a new training data set. Yeah.
Like one thing that I'm kind of confused about is that the labels that we attach to these images are kind of random, right? Like when in this meta testing setup, when we're trying to predict these labels, then how is the network like kind of backtracking and matching them to what the image actually was? So is it kind of like it's just matching those two values of alpha?
So you're asking what is the neural network doing?
So
What it be?
So
I guess I don't have because this is black box, I don't have a great sense for exactly how in practice the neural network is implementing it, is choosing to implement this. It does have to store information about how you map images to labels, and like what is like zero, what does label 0 mean from an image? Or it could be, I mean, there's a lot of things that it could be doing. It could be actually, like, if it's a really huge neural network, it could be mimicking something kind of like gradient descent, for example. So it's a little bit hard to understand in general. Yeah.
I think my question comes from the multitask learning. So here we know that we use some classes to train our neural network and then test it on some classes. Is there any way, again, to know which classes would actually help during training, like which classes would actually help to use during training so that we get the better result?
Yeah, so the question is there a way to tell if certain character classes or certain tasks would be helpful in for a particular test task?
Not in general, so like for languages, we do know that languages we have different, so it's like a common set. like when there's a huge bunch of data defined with different variation of classes, how would we know?
Yeah, so if you have tons of tasks, then there's going to be kind of more heterogeneity in terms of when one task might be helpful for the test task. But yeah, in general, we don't really know. It's kind of similar to fine-tuning and multi-task learning. And maybe you should figure it out for your project and then tell us all how to do it. Cool. So I went through a lot of that on the whiteboard because I felt like that would be easier and kind of more intuitive to walk through. The slides have basically everything that we went through on the whiteboard. So version 1, we're going to be training a neural network to output these parameters. And then we're going to be predicting test data points using a neural network parameterized by those parameters phi I. And you can think of the first network as kind of the learner. It's learning from these training data points. And the second network as something that's actually making predictions using those parameters. Here's the RNN that we drew on the board. This is representing F theta. And then here's the kind of the second part of the network that we drew on the board as well from the test examples. And then we can train this, train the parameters of theta with standard supervised learning. In terms of what the loss function looks like, negative log likelihood which is cross entropy loss or mean squared error, is the loss function that's typical to use for supervised learning. And so that's basically the loss function that will be applied right here to backpropagate through. And you can, if you think about this as the loss function for task I, then you can basically view kind of this overall loss function as making a prediction for task I and then evaluating that on the test data points for task I, and then averaging that across the tasks. I want to go through this somewhat quickly because this is basically stuff that we all went through on the board. We sample a task. We can also sample a mini batch of tasks rather than just one task. We can then sample disjoint data sets. So this would be like our training set and our test data set from all of the examples that we have for a particular task. I should mention maybe here that it's worthwhile to kind of mix and match these. So you shouldn't always use this as your test examples and always use this as your training examples. You can get a little bit more data for meta training by randomly sampling what you use as a training example and what you use as a test example. And so kind of visually what this looks like is maybe these are all the examples you have for one of your tasks. You want to allocate this into training examples and test examples. And so you'll kind of just randomly assign them to a train set and to a test set. Cool. And then once you have your train set and test set, you can compute the parameters and then update, compute the parameters with the forward pass and then update the meta parameters with the backward pass. And then repeat. Cool. We talked about how outputting all the neural network parameters isn't very scalable. And so instead of doing that, you can just only output the sufficient statistics and use another, basically replace phi I with hi and have this be a lower dimensional vector and have that be combined with some other meta parameters in order to make a prediction. One thing that's kind of intuitively nice about this low dimensional vector is you can think of it as representing contextual task information. And so if we remember back to multitask learning where we had this task descriptor zi, you could sort of think of hi as a form of task descriptor that we're inferring from data. And then we're just going to be passing that hi into a neural network in order to make predictions for that task. Yeah.
How many tasks, like in the test set, do you need a test on to make sure it's effective at working on tasks? Because they might be quite different. So how do you know that your test set is a good representation of how well it would do on another random task?
Yeah, so the question is, how many test tasks should we use when we're evaluating a meta-learning algorithm? And so, yeah, in general, you don't want to just have one target task when you're evaluating. You want to have like at least a few. And one thing that you can do to get a sense for how many you need is you can look at the variance of the accuracy across tasks. And so if one task you're seeing it has like 80% accuracy, another task has 100% accuracy, and another task is like 0% accuracy, then your variance is pretty large. Whereas if they seem to be more or less consistent across tasks, so that maybe is a good indication that you may have enough tasks to get a good reading on it. Yeah.
How do we learn the big theta G for phi I?
Yeah, so the question was how do we learn the big theta G for phi I? So you can think of theta G as part of the meta parameters. And so that's actually why I'm using theta here. So we're going to optimize theta G alongside all of the rest of the parameters of theta. And so that's how we make it possible to have HI be only a low-dimensional vector. Likewise, theta G may have some parameters that are shared with the kind of the other part of the recurrent neural network. Because, for example, you may have like the encoder of the image be the same for these training examples and test examples. Yeah?
Is there a ballpark for how much less data that you need for each task with meta learning versus like training an individual model?
Yeah, so is there a ballpark for how much data you need? So with meta training, and as you'll see in the assignment, you can go down to as few as one example per class if you have a lot of tasks. And so the per task, you can go down as to something very, very small if you have a lot of tasks and if they have shared structure. That said, if you only have one example per class, your total amount of data may still be somewhat similar to kind of single task learning in that you may have a lot of tasks. And so you may have a small amount of examples per task, but a lot of different tasks, so your total data may be somewhat similar. And then, of course, the amount of data you need will depend a little bit on the complexity of the problem you're solving. Cool. And then I said I would talk a little bit about architectures. So we talked a little bit about RNNs before. One of the first papers that introduced this, at least more modern notion of meta-learning with kind of black box neural networks is this paper right here. And this is from 2016. This is actually sort of in response to a challenge, basically the Omniglot challenge being released and some cognitive scientists saying neural networks can't do few-shot learning. And this paper showed that, oh, neural networks can actually do few-shot learning and was able to do pretty well on the Omniglot data set. They used LSTMs and neural Turing machines. I wouldn't necessarily recommend using neural Turing machines. They're, I think, a little bit of a relic of the past. But yeah, it's worth mentioning this is one of the first papers. And in your homework, I believe we have you using LSTMs in the homework. But if you want to, you can also play around a little bit with transformers. Another architecture, which is called a deep set architecture, is to, instead of having a recurrent neural network, instead pass all of your examples through a feed-forward neural network to get an embedding of each of your images, and then average those embeddings to get a kind of a summary vector. I sort of already answered this earlier, but I guess I can see if you're paying attention, which is why would something like feed-forward and then average be better than a recurrent neural network? Yeah, so it's permutation and variance. So yeah, so averaging is agnostic to the order of the things that you're averaging. And so this sort of architecture is permutation and variant. This is an architecture called deep sets. One thing that's actually pretty cool about deep sets is there's a result that shows that for some conditions on the width and depth of the network, these kinds of architectures can represent any permutation and variant function. And so while it may seem actually somewhat limiting, these architectures are actually very expressive as long as you only care about permutation and variant functions. There's also other external memory mechanisms that have been proposed. And then there's also papers that have proposed things that use attention and convolution. This paper came out before I think transformers, or certainly before transformers were popular, and so they probably would have called it a transformer or something. And then there's probably more recent papers that actually use things like transformers as well. And then these methods can do pretty well. So on the omniglot data set, if you use this architecture, which uses attention and convolutions interleaved, on omniglot, on 5-way, one-shot omniglot, you can get 99% accuracy. If you have 5 examples, you can get even higher, 99.78% accuracy. If you make it a little bit harder and you're now doing a 20-way classification problem, then you can still get accuracies in the high 90s. So omniglot is not too difficult. And then if you look at something like mini ImageNet, which is a smaller version of ImageNet with smaller images, you can start to get somewhat reasonable 1-shot and 5-shot accuracy, but these numbers are a lot lower than omniglot numbers. And they're also certainly below state-of-the-art. Yeah. But we'll see some things that are closer to state-of-the-art in the next 2 lectures. Yeah.
About like why do external memory systems are being used for meta learning? Like how do they help in meta learning?
Yeah, I certainly don't think that they are necessarily things like neural Turing machines and these other external memory mechanisms. I guess I wouldn't necessarily recommend them. I think that they're possibly interesting from like a neuroscience standpoint because I guess I'm not a neuroscientist, so maybe I shouldn't talk about this, but I think that there are aspects of the brain that kind of store memories. And so if you want to think about kind of key value storage and kind of storing things in that way, these things may be interesting. They also perhaps have some benefits from the standpoint of like maybe kind of memory footprint, because if you can very efficiently store that information, then maybe you don't need kind of this really big transformer. But we haven't seen, that's somewhat speculative, and we really haven't seen a lot of benefits empirically from using them. Cool. So in homework 1, there's going to be some key things that the 2 key things that you'll do is implement the data processing. So implement how do you actually like split things up into tasks and examples per tasks, and then also implement a pretty simple black box meta learner and train that on omniglot and get some results. Cool. So in terms of just to kind of also sum things up and talk about some of the pros and cons of this approach, one thing that's really nice about this kind of approach to meta learning is that these big neural networks are quite expressive, and they can represent lots of different learning procedures. RNNs can represent, if they're large enough, they can represent really any function. They're also really easy to combine with a variety of problems. Today we talked about supervised learning, where you backpropagate the loss with a supervised objective, but it's also very easy to plug this into reinforcement learning objectives as well, because maybe it's outputting not the label, but an action or a Q value. And you can train this just like you would train a recurrent neural network with kind of reinforcement learning objectives. In terms of the downsides, these big networks are somewhat complex, and they have to learn something pretty difficult, which is learning from data points. And this can lead to somewhat of a challenging optimization problem. And as we'll start to see in some of the next lectures, optimizing, like trying to learn how to learn from scratch from kind of randomly initialized RNN weights can be pretty difficult in comparison to giving it some of the structure of learning algorithms that we already know. And so as a result, because it's a hard optimization, these can be less data efficient than other meta learning approaches. Cool. So there are other ways that we can represent F theta. And so next time on Monday, we'll talk about what if we treat F as an optimization problem and actually embed optimization into F rather than having this big RNN. Cool. So now I'd like to talk a little bit about large language models and things like GPT-3, Chinchilla, and the latest Gopher, Palm, the biggest language models these days. And we're going to focus on GPT-3 just because it's a fairly canonical example. And they also have lots of really cool qualitative examples in the paper that we can draw from. And things like GPT-3 are a lot like kind of a black box neural network. But one thing that's a little bit different from here that we'll talk about is that they have, that few-shot learning kind of emerges in a way that wasn't explicitly, I think that when you train a language model with a language modeling objective, you're not kind of setting out for few-shot learning. You're not setting up the data to train it to do few-shot learning. It's something that kind of emerges from the data in a somewhat more surprising way. And so we'll talk a little bit about emergent versus the kind of few-shot learning we see here. So GPT-3 is a language model. You can sort of think of it as a black box metalearner or a kind of a big RNN transformer neural network that's trained on language generation tasks. And you could sort of think of it as where detrain corresponds to a sequence of characters, and detest corresponds to the following sequence of characters. And so detrain is what the language model is being conditioned on, and detest is what it's being trained to generate. The data set corresponds to crawled data from the internet, English language Wikipedia, and 2 book corpora. And the architecture is a very large, well, I guess by these standards, by these days it might be considered somewhat small, but in my opinion, a somewhat large transformer neural network. And so it has 175 billion parameters, 96 layers, and a pretty large batch size. What do the different tasks correspond to? So this is something that, this is where kind of emergent few-shot learning comes into play. So you can see it do tasks like spelling corrections, simple math problems, translating between languages. And these tasks are in some ways somewhat emergent, but also in some ways reflective of the kind of data that you see on the internet. And the cool thing about things like language models is that these seem like, on the surface, these seem like very different tasks, like math versus machine translation versus spelling. And we can actually have all these tasks solved by a single architecture. So the way that you can do that is to put them all in the form of text, put them all in kind of a common language for the network. And that's a good idea because it's also very easy to get a lot of data of text on the internet. And so what this looks like is you have an inner loop and an outer loop. So in here, kind of a forward pass of our RNN was an inner loop, and training that RNN to learn was our outer loop. And so likewise here, in context learning, kind of running the RNN on text is your inner loop. And then across, when you see across tasks and optimizing the neural network across to these different tasks is the outer loop, and that's kind of the learning process of optimizing the parameters of your big transformer model. And so these are kind of the example tasks that we saw before, all in text form. Cool. And so they trained this on data from the internet and Wikipedia and so forth. And you can get some pretty cool results. So you can see something like one-shot learning, where you give it a dictionary definition saying to screech something is to swing a sword at it. An example of a sentence that uses the word screech is, and then it gives you a sentence, we screeched at each other for several minutes, and then we went outside and ate ice cream. So this is like one example of one-shot learning. You could also do few-shot language editing, where here you give it 5-ish examples of poor English versus good English. And once you give it those examples and then give an example of poor English input, I'd be more than happy to work with you in another project. The good English output that corresponds to that it gives you is, I'd be more than happy to work with you on another project. And likewise, you see another example for the same prompt at the bottom. And then it can also do things that aren't really considered few-shot learning tasks. So you can ask it to write an article for you given a title and a subtitle. Cool. So some things about GPT-3 is that the results are really impressive. And also, since GPT-3 has come out, there's actually some models that do even better by a pretty significant margin. GPT-3 and other more recent models are also far from perfect. They make mistakes. So GPT-3 itself, even the largest model has an accuracy around 50 to 60% on few-shot learning tasks. I think that things like Chinchilla are maybe closer to like high 70s, but still have a lot of room for improvement. They also fail in somewhat unintuitive ways. So if you ask it how many eyes does a giraffe have, a giraffe has 2 eyes, how many eyes does my foot have? It starts telling you things like your foot has 2 eyes, and a spider has 8 eyes, and so forth. So yeah, it doesn't fail in the same way that humans fail. And then the last note here is that the choice of detrain, like basically how you prompt the model, how you give it these examples, is also quite important. And we'll see an example of this. Well, you'll get to play around with this a little bit in homework 3. And then the last thing I wanted to mention about these models is that there's some recent research on actually trying to understand when will few-shot learning emerge from these data, from these kinds of models that are trained on text data. And the research has shown that both aspects of the data and the model is important. So it has shown that having temporal correlation in the data is important. And for example, if detrain and detest are completely independent from one another, they won't actually learn to use that context, and it will just ignore that context. And so they think of this as kind of having kind of bursty data in time versus non-bursty data. They also find that having a dynamic meaning of words is helpful. If there's a word that kind of means different things in different contexts, like the word wicked might mean something like evil in one context and something like really cool in another context. And that can help with few-shot learning because that encourages the model to actually pay attention to the context when making future predictions. And then also there's some work suggesting that different aspects of the model are important. The biggest #1 thing is that the model has a high capacity. People have found that transformers are much better at giving you capacity than things like LSTMs and RNNs. And so here's a plot of kind of few-shot learning accuracy for these different architectures. And then also larger transformers are better than smaller transformers. In the GPT-3 paper, they showed that like a 175 billion parameter model was much better at few-shot learning than some of these smaller models. Cool. So yeah, that was it for today. We went over black box meta learning and saw how we can train neural networks to do few-shot learning. As a couple reminders, your project group form is due on Monday, and homework 1 is due on Wednesday next week.